All right, so part one, the smaller features. Now we're moving into the little bit larger features, are the ones that have more parts that interrelate. So next feature, supporting better class design. Default, delete, override, final, and all this stuff. Historically in C++, what you had to do in order to prevent a type from being copyable was not ideal. There were really two approaches. The universal approach, one that doesn't require some additional library support, is to declare the copy operations, right? Copy constructor, copy assignment, private. That would prevent an RHC object from being copied, and it would be prevented at compile time for most people, for non-developers of the class, or not, for non-member functions trying to do a copy, it would be caught and be an error at compile time. But for code that's inside of member functions or friends, it wouldn't be a violation of privacy. And then it ended up being a linker error because you don't actually define these, you just declare them. So it would be an error, but later. And it's not really ideal to have link errors. You'd rather have something like that diagnosed at compile time. So an approach that does give you the compile time support across the board is to inherit from something like boost non-copyable, which is basically a base class that does this. If you inherit privately from it, now it's illegal to attempt to copy an RHC no matter who you are. So those were the two approaches that worked because there was no real better way to do it. In C++11, there's a much cleaner way to do it. So these new specifiers, equals default and equals delete, can now be tacked onto the generated function declarations. So this only applies to functions that would have been generated or not by the compiler. So default constructor, copy assignment operator, and destructor are the functions you can specify with equals default and equals delete. If you say equals default, the compiler generates the same function it would have generated had it done it on its own. Remember, if you declare a constructor that's not a default constructor, right, then the compiler will not generate a default constructor for you. So there was no way in old C++ to declare some other constructor and then let the default constructor be just generated in the default way. You had to actually provide your own definition. And that wasn't usually a big deal, but it was one more thing to remember. Now you can just say equals default, and the compiler will generate the one it would have generated if you declared no constructors at all. You can also say equals delete, and this solves our problem of disallowing these operations. Well, the cool thing about this is that it's still public. So the access control doesn't have to be hacked to make that an error. It's still public, but it's deleted. So if anybody tries to perform a copy operation, it's immediately diagnosed with a nice message that clearly tells you this operation has been deleted. That's why you can't do it. Default construction is fine. Direct construction here with a string is fine, but any kind of copying operation is now diagnosed at compile time. Something I learned relatively recently, you can also apply equals delete to restrict overloading of functions. So if I just declared do something of int, and that's the only thing I did, you could pass anything that converts to an int as a parameter, right? All of these would basically compile if all we had was this one declaration. But if you want to disallow, say, longs and doubles, now you can do that explicitly. Just say equals delete. And there was no way to do that previously. You could declare the function and then have it throw an exception or something, but that's ugly. So this provides nice, efficient compile time support for restricting the values that are allowed to be provided in those situations. All right. So this slide is a compendium of ways to make mistakes in old C++. Let's say we have an inheritance hierarchy, a base and derived class. The base class has virtual functions f, ff, and g, and a non-virtual h. And let's say you're looking at this derived class definition here. And there's some things you'd like to know. looking just at the derived class, can you tell if this f here is a virtual function or not? No. I mean, you have to know what the code says up here, right? So there's not enough information here to know that. Looking at this, we don't have to ask whether it's virtual or not. That's now obvious. But was this intended as an override of a base class counterpart, or wasn't it? You can't tell by looking at this. How would you prevent a class deriving from derived from overriding FF? There's no way. And looking at this, does this override bases H? Again, looking at this, we just don't know. So all those questions can be answered by looking at the code up here. It's not like they're a big mystery. But it would be nice if you could look at a derived class in isolation and still be able to glean that kind of information from it. And that's what C++11 provides. So 2 new keywords, and I'll have something to say about the fact that they're not ordinary keywords, but override and final can now be used to make it very clear what is your intention in your derived class. So up here, the base class is the same as it was before, and I'll get to this comment in a minute. It's just a comment. All right, so the question was, does F override a base version? If this compiles, it does. So the override says, really, I mean for this to be an override. And the compiler enforces that. So if F is non-virtual up here, or if it has a different signature and there's no base version of this signature that's virtual, this will not compile. If you don't want to let a derived class override, you can now just put final here. Unfortunately, it only applies to virtual functions. But at least you can do that for virtual functions. Now, was this meant to override a base? Well, if we put override here, the compiler will let us know if it's not an override. So forgetting to put const. Something's wrong. Either this const wasn't supposed to be here, or this was supposed to have a const. One of the two. Regardless, the compiler will give you the diagnostic. All right, now let's look at this last case of H. For the first 3 years or so I presented this talk, I had this final here. There wasn't a semicolon. The semicolon was after the final. And I was so happy that I could do that. And I found out not that long ago that, in fact, I could never do that. And it was wishful thinking on my part, because one of the classic problems in C++ is a non-virtual function being redefined, right? This isn't an override. The word override only counts when it's a virtual function that you are redefining. So unfortunately, this is still legal, and there's no way to prevent it. It would have been nice if you could put final on here, but alas, it doesn't apply to non-virtual functions. So this is still a hole, sort of in the class mechanism that you can fall through. So that's the bad news. So let's end on some good news. Notice the word final is not very obscure looking. In the past, when the standard introduces new keywords like dynamic cast or something, they tended to be obscure enough that they weren't likely to just accidentally collide with some identifier somebody had in their code base. But final, even override, those look kind of dangerous for new keywords, right? The key is they are contextual keywords. They only apply as keywords in this particular set of contexts, which is right here in a function declaration. And if you use them anywhere else, they're not keywords, and old code that has a variable called final will continue to run. In fact, you can have a function named override with the override specifier, and that's fine too, because it's only a keyword in this exact place. And so it conflicts with nothing. Question?
So why does G error? Is that because...
Why is this G an error? Because up here it's a const member function, so that's part of its signature. And so this is not an override of that. It would have to have a const here, or this one would not have to have a const. Then it would be an override. The constness is part of the signature, just like the parameter types. OK. So that's that. Also, an entire class can be declared final. So you can make a class illegal to derive from. Just put final where? Oh, derived is final. Oh, here it is. Jeez. So putting final here means this is a final class. It is illegal to derive from it. All right, for the next example, we're going to use flux capacitors. And old C++ constructors cannot call other constructors. This is a feature Java has had from the beginning. C#, I think, has it as well. C++ was kind of the holdout. And that meant that code sometimes had to do extra work, and bugs could seep in because of the inability for constructors to call each other. So let's say a flux capacitor has a ordinary data member capacity, and it has an ID number, and it calculates the ID number by incrementing a static. So every new flux capacitor gets the next value of next ID and stores it in ID. And there's a way to validate flux capacitors. So a default constructor would set the capacity, set the ID. A flux capacitor takes a double, would set the capacity. It would silently convert to a complex, set the ID, and then validate. The copy constructor, the constructor takes a complex, would set the capacity, set the ID, and validate. The copy constructor doesn't have to validate, but it sets the ID. And this compiles. Anybody spot the silent error here? OK. Notice that we're not setting the capacity for this constructor. Or it's not copying the capacity from F, right? So the capacity is going to be default constructed here rather than copied from F. So that's a silent bug. And the interesting thing about this is when I first wrote this slide, I actually committed this bug accidentally. It wasn't on purpose. And then a fellow instructor pointed it out to me and suggested you should leave that like that because it shows how easy it is to make a mistake when you're dealing with all this bookkeeping, right? OK. So in C++ 11, constructors can call other constructors. Again, it's not a silver bullet, but in some situations it might be helpful. So in this case, the constructor that takes the complex does the heavy lifting. It sets the capacity. He can't forget to do it now. It sets the ID, and it validates. And all the others will simply defer to that one, or to one that defers to that one. And because these are all inline, it's going to be efficient. Right? There's not actually a bunch of calls involved. So the default constructor actually doesn't have to do anything else because it just sets the it defers to the one that takes a double. So the default constructor will call this one. The constructor takes a double will defer to the one that takes a complex. So either way, for both of these, you end up down here. The copy constructor is going to read the capacity out of F and then invoke this constructor to do that as well. So there's very little duplication of effort. Nonetheless, there's still one subtle performance hit you could argue about this approach of this particular example. And some of you may have noticed it. And that is that we're validating things like setting the flux capacitor to 0.0, where you might argue, well, 0 is a valid value. There's no reason to validate it. But you end up down here to do everything, including validation. So again, it's not a perfect scenario, but you can select from 6 of one, half dozen the other, whatever, and pick the one that's the best fit. And if you want to use this facility, it's there. At least it will be there. This is like one of the last features that compilers tend to add in terms of feature support. So I'm not sure I've seen a compiler that actually supports this yet. It probably will be soon if there isn't already. All right. In old C++, the only type of data member that was allowed to be initialized in class is a static const integral type of some type. So ints, shorts, bools, those could be initialized in the class. The most common use case is when that value is going to be used as a dimension for an array. It's convenient to just stick the number here so you can refer to it down in the definition of the array, right? So static const integral size t, number of cells. And then we can use it to dimension an array. But there's no other types of data members that you can initialize in the class itself, in the class definition. So an ordinary data member, you can't do it. A static data member, you can't do it. That was a limitation. In C++11, any non-static data member can be initialized in its declaration in the class definition. So in this particular case for ID, I didn't bother giving it an initialization. I wonder if I could have gotten away with it somehow by using next ID++. I never actually thought of trying that. But in this example, I just didn't put that here. I let the constructors do it. But the capacity, I provide an initial default value of 100. So the way it works is if the constructor actually initializes that data member in its initializer list, and the key is it has to be in the initializer list to be considered an initialization, right? Are we familiar with that? If it happens in the braces, it's not an initialization. It's an assignment. So as long as it's initialized up here in the initializer list, code will not be generated to throw 100 into it. The compiler knows it doesn't need to do that. It'll do whatever you say up here, set it to C. But if you don't mention it up in the constructor, like in the default constructor, we don't mention C. So an object default constructed, a flux capacitor default constructed, will have its capacity set to 100. Unfortunately, it's still illegal to initialize a static data member in class. And as far as I can tell, that's because it still needs to be defined out of class, because that's one of the rules of the language. And so if it needs to be defined out of class, that's the logical place to give it an initial value. And it doesn't let you do it in here. It's kind of too bad, because it's like the one little exception. It's like you can't use final on a non-virtual. The one little exception, right? Just to keep things interesting. But it does let you do all the rest of them. In new C++, you can even inherit constructors from the base class. So it sounds a little strange. Why would you ever want to inherit a constructor? Don't think of it as literally inheriting the exact same constructor. Think of it as inheriting all the functionality of the base class constructor and having it just built in implicitly to your code. So let's say we inherit from flux capacitor and we introduce a red-black flux capacitor, which is just like a flux capacitor, except it can also either be red or black. So a data member is just a color, and it's initialized to red by default. This syntax here says I'm inheriting the base class's constructors. This syntax is not really new for C++11. It's just using the name of the class itself. Used to be illegal, but it was illegal for all the other member functions. You can say using base : name in C++98, but the exception was the constructor wasn't legal. That restriction has been lifted, so now it is legal to use the constructor name. And the effect is you're inheriting the functionality of all of those constructors. And then we add a constructor that takes a color. So what this is going to do is still going to call the base class default constructor and do what that does, and it's going to set the color to C. But if you use any of these other constructors from flux capacitor, they'll do what they do, and the color will be set to red. Does that make sense? It's just another little trick to avoid having to re-specify the same code, reinvent the wheel. The term user-defined conversion. You guys heard that term? Right, in C++, old C++, there's basically two types of user-defined conversions. Constructors that can be called with one argument, which are a conversion from the argument type to the class type. And the compiler will invoke it implicitly unless you say explicit. So that's part of old C++. And the other type of user-defined conversion is an operator function. And that's a function of the form operator type name open close. And whether or not it has const is optional. So that's that is a conversion from the class type to this type. So when I teach kind of introductory C++, or I try to go over best practices, I usually dissuade the use of operator conversion functions at all, ever. Personally, I like the idea of just creating an ordinary function like toDouble to perform that task, because this is completely predictable. It only gets called when you ask for it. A client actually has to write some object .toDouble. Whereas this thing gets used implicitly, and sometimes that causes nasty surprises. In old C++, these were always implicit. So what C++ 11 added is the ability to declare them explicit, just like constructors. It's an improvement. Now, it won't silently apply one of these. You actually have to ask for it. However, I personally still think it's better to just use toDouble. But that's a religious issue. So that's just what I happen to believe. Operator bool, question was what are operator bool? Well, that one's kind of a special case because it's so common for things to be evaluated in a logical context that there's a whole bunch of separate issues around that, which we don't have time for. Yeah. Like I said, explicit is an improvement. Okay, and perhaps operator bool is one that you can make a good argument in some environment is a good idea. But somebody else might be able to come up with the opposite argument as well. Okay, so that was that. Larger language features. Initializer lists, uniform initialization, prevention of narrowing. All this has to do with initialization, lambdas, and move semantics. I love talking about move semantics. I'm going to work really hard to make sure I have enough time to do that. So let's move on. All right. This type of construct is known as an aggregate in old C++, and the two types are arrays and structs, right, that you can, or in C actually. Those are C aggregates. And their syntax is available in C as well, both old and new. So here's an array that's initialized and a struct that you can have its members initialized. In old C++, vectors, STL containers could not have brace initialization. So that's been addressed. What you had to do is first you declare an array, and then you initialize your STL container with a range, right, which is the beginning and one past the end of the array. So that was the classic approach, and it was clunky. It works, but not ideal. So new C++ introduces the idea of initializer lists, a way of supporting generalized initialization of aggregates. And it's an extension of the old array object initialization syntax. So now we can initialize an STL container, a vector with specific values. And the equal sign is optional. So I think the conventional style in new C++ is to omit the equal sign. But there's no difference functionally here. The interesting thing about using the term initializer list is it's not just for initialization. So this is not an initialization, is it? Assuming v2 means this v2, right? This is an assignment operation. It's replacing the contents of v2 with the elements of this construct. So the construct itself is an initializer list. It's basically being used to initialize itself. And then its values are propagated into v2 via assignment. It's assigning the contents of v2. So sometimes calling it an initializer list is a little confusing, but that's still technically what this is. So how does that work? A little peek under the covers. Before we peek under the covers, a question. Yes?
I was going to ask if that uses the assignment operator.
Yes, here it is. So here's the implementation, more or less, of how this looks. If you go into the vector.h header file, you'll find that there's a constructor that takes an initializer list and an assignment operator that takes an initializer list. So this form, both of these, in fact, use the constructor here, and this one compiles into operator equals. And the library does it, and so can you in your own types. So more on initializer lists. Here's a function foo that returns a vector of int by value. Now, in old C++, that would raise eyebrows, right? Seems inefficient. But as we'll see in new C++, it's not necessarily inefficient at all. Anyway, inside of foo, we have a vector event, which we'll initialize, and then we'll mess with it, adding some values at the end. And here's a range-based for that uses an initializer list of stuff and does something with it. We actually saw this before. And then finally, we return this initializer list. So this thing has no type, as Scott said this morning, right? And that was news to me. I didn't realize this has no type as a syntactic construct. But it serves as a valid source of initialization for this temporary that's returned from foo. So this actually constructs a vector event initialized from this initializer list, and it returns it by value. At the calling site, we just say foo. So this returns a vector with these values in it, and then we can iterate across it. And for reasons we'll see a little later, it's not necessarily inefficient at all. Even if this was 10 million elements, it probably wouldn't take a whole lot longer than this code does. Question?
But wasn't returning by value good before as well because the RVO?
Yes. So the question is, wasn't returning by value good because the RVO would get in and help you out? If the RVO could, yes. The return value optimization was an optimization. It still is. And if you're familiar with it, it's still a useful technique that compilers use and will continue to use. It's the cases where the RVO doesn't apply that move semantics, which is what this is leading up to, benefit. So there's a bunch of different pieces in the puzzle. There's the use of the RVO and the different kinds of RVO. There's ordinary copying, and then there's move. And the compiler juggles them all and comes up with the best possible fit. And you can facilitate that, right? You can help the compiler make the right fit. Constructors taking an initializer list are preferred over ones that don't. Again, a lot of this stuff that is the danger is stuff Scott talked about this morning, so this should look familiar. Vector has a constructor that takes 2 values, 10 elements, each equal to 20 here. And if you make the mistake of putting that in braces, the compiler will see this as an initializer list of 2 elements, which might not be what you intend. So I believe Scott explained, and I agree, that this interface in vector is, by today's standards, a bad quality interface. You should never design classes going forward where using braces instead of parens will cause this type of confusion. So basically now everybody wishes that the vector class didn't have this constructor, right? But we're stuck with it, and it's just a pothole we have to watch out for, that's all. So this slide is another example of all the ways in which initialization syntax from old C++ could be confusing and maybe not intuitive. If I say new int 10, that gives me a pointer to a dynamically allocated int initialized with 10. Fine. New int gives me a pointer to a dynamically uninitialized int, if that's what you want. If you put the parens here, it value initializes. So it'll be a pointer to a dynamically allocated int equal to 0. Those are fairly straightforward. But if you looked at these and then you apply it to a non-dynamic, int v1 10 kind of corresponds to this. It's an ordinary local initialized to 10. Then you might think this should correspond to that, right? But this is the most vexing parse, as Scott coined the phrase. So this is actually a declaration of a function taking no arguments and returning int. Common newbie error in C++, newbie or otherwise. If I looked at a piece of code like this, what is this saying? Like, what is foo? You can't know. You have to know what bar is to know what this is doing. Because there's 2 things bar could be, right? It could be an int or something that's a value type that converts to int, or it could be the name of a type. So this could be either a variable initialized from bar or the name of a function called foo that takes a bar and returns an int being declared. You just don't know. It's perfectly legal in old C++ and in new C++ to initialize I, which is an int, with 5.5. Isn't that lovely? It's also perfectly fine to initialize an integer with a value that can't possibly fit. Isn't that lovely? historical reasons, right? That's just the way it's always been. None of which is very pretty. So C++11 introduces uniform initialization. The idea being, by finding a new syntax, we eliminate a lot of this ambiguity. Braces are used only for initialization. No, I'm not talking about those. Okay. Braces here are used only for initialization. So this still initializes that int to 10. So does this. This is still an uninitialized int because the code has to have the same meaning as it did before. This, however, is absolutely unequivocally an initialization of v2 with its default value, which is 0. This, well, now we see the type def. So now we know this is a function declaration. With braces, it's an error. The compiler says, hey, this can only be an initialization. You can't initialize foo with a type. You can only initialize it with an expression. So, error message. And now, fortunately, thank you, these types of things are illegal. Now this one you can argue it's pretty safe to make that an error. It's hard to believe somebody would actually want the compiler to try to shoehorn that value into an int. This one, a little less obvious, but still a good idea. Because after all, why would anybody write an initialization of an int with 5.5? So if you use the braces, the compiler just says, this makes no sense, that's an error. There's no way you'd ever want to do that. Question?
Can you, instead of 5.5, can you initialize that with a variable that was equal to 5.5 a double? That still causes an error.
Question, can you put a double variable in here? Still an error, absolutely. I just used constants because it makes things go fast. But a lot of these things where there's constants can be variables, runtime values. Be careful when initializing aggregates. Remember, aggregates are C-like arrays and structs. There's some breaking changes involved here. Narrowing and truncation of aggregates is always an error in C++11, even if it's using syntax that was perfectly fine in C and in C++98. This is something you have to watch out for. This is also one of those situations where if you still have code like this, you should not be upset when you get the error message, right? It's like you'll look at it and go, why did I ever do that? It makes no sense. That's why I think it's OK. So here's a struct, which I initialize with 5 and 10. That's OK everywhere. And without the equal sign, it's OK in C++11, right? But in old C++ or C, it's not. It's an error everywhere, but for different reasons to have a mixture of these types here. So, and because of the double. I mean, it's not that it's a mixture, it's that one of them can't possibly be converted to an int in a rational way. So this is an error in C++98 because of the lack of an equal sign, and this is an error in C++11 because of the narrowing conversion. Two different reasons. Struct initialized with this, OK. Error in C++11 because of the narrowing conversion, still OK in old C++. Right? If you're running under a C++98 compiler, that's fine. So this rule, the not allowing truncation is a C++11 and forward issue. All right, last one. Here's an old array of ints. Error in C++11 because of the narrowing, truncation. Fine in old C++. Because old C++ lets you do stuff that's ridiculous. All right. So another little gotcha while we're talking about gotchas. Initializer lists in auto don't play nice. This successfully initializes A to 10 as an int. And if you use the RTTI, it'll tell you that it's an int. That's what I means. But if you use auto B brace 10 brace, it compiles, except the type of B is actually an initializer list of int. Don't do that. unless you want an initializer list of int. That's the moral of that story. All right, let's move on to lambdas. So here's an ordinary function, and we can use that with an algorithm like find if. No big deal. All right. If we don't like having to create a new function for something as simple as comparing a value to 0, there's library support in old C++ for doing it with these built-in function objects, function object templates, and binds, and all that. You can get away without having to write a new function, but it's a little less than intuitive, right? But you could do it. So those are some of those options for doing that in old C++. Another option in old C++ is actually write an explicit function object class and instantiate it here. And in fact, this is, I think, pretty much the accepted best way to do it in terms of performance and clarity. And it has a lot over the previous slide, but it's not perfect because there's a separation between the use of this thing and its implementation. That might be in different pages of your source code, and somebody looking at this code has to flip back and find where that is. And I know with context-sensitive IDEs and all that, maybe it's not that hard to do that anymore, but there's still this separation. It'd be nice if the functionality, which is really just this test, was very apparent right here, and not just through the name, but through the actual code. And that's the motivation behind lambdas. A lambda expression lets you write an anonymous on-demand function object. A lambda, which looks like this, actually generates code that kind of looks like this, except you don't know what that name is. And then instantiates an instance of that class and sticks it right here where you need it. So everything that's important is right there where you care. So this will go through this container, this sequence, and find the first value where n is greater than 0. So I didn't delve into the syntax yet because I just want to give a bird's eye view of the whole point of this, that it's an intuitive way to express something that there was no way as clear as this to do before. It was like 3 different evils you had to pick between. All right, so that's the basic syntax. It's introduced by the square brackets, and in this case they're empty, but as we'll see, you can put stuff in there. And then this is the parameter list to that function object. Remember, a function object is something that can be called as a function. So if it's a function, it has an argument list. That's the argument list. And then this is what we're doing with parameters that were passed into it. All right, so that's kind of the simplest basis of lambdas. Now, because the mechanism actually creates a class somewhere, and that class is in a scope that's different from the place where it's used, there's issues of access to data that was local to that calling scope, that place where the lambda was actually used, that is no longer in scope where the lambda actually lives. So there's a mechanism for making the lambda have access to stuff that's in the calling scope, and that's called the capture list. So in this case, I stole an example from one of Scott's examples in his effective C++ courses. He has a within epsilon concept is a way of testing a value. In this case, we're going to test each of these values in the vector to see if they are equal to 4.9 plus minus 0.3. So they're within 0.3 of the value of 4.9. So a way to do that, and we're going to actually use the partition algorithm. So all the values that are within that range are going to be on the left. All the ones that aren't are going to be on the right. So we're going to partition the container, and the comparator, or the function object that compares the values. I guess this isn't a comparator, it's not sorting. The predicate is going to have access to target and epsilon because it needs those values in here to do the calculation. So once it's got access to target and epsilon, it calculates whether something is within epsilon by applying this computation to it. So these variables are actually copied into the closure, which is the term for the function object created by the lambda, and then they can be accessed. But they're copies. So they're not the same values here. They're not the same object, they're just copies of these objects. And then at the end, I use another lambda to actually display each of the values. I use a for each, and I apply this lambda to each element just to display its value. Question?
If you need to modify target and epsilon, you have to pass a reference.
Yes, the question is, what if you wanted to modify this target in epsilon? You pass it by reference. I'll show you how to do that in the next slide. Next view. Okay. So the capture list gives you some flexibility. If you just put the names of variables, a name by itself is implicitly it's being captured by value. Copy of the original one is copied into the closure. If you put an ampersand, then it becomes a reference to the original, and that allows you to go and modify it. So in this case, both of these variables are captured by reference. In this case, this one is captured by value, this one by reference. If you just put an equal sign, that means by default, use value capture for everything. It's as if you listed every variable like this. And if you put an ampersand, it's like you listed each variable that you use like this. If the outer scope has 50 variables and you only need 2 or 3, it's not going to capture all 50. It's only going to capture the ones you actually use because the compiler can tell which ones you actually use. So it won't waste time capturing things you never even access. And you can even have a default and exceptions to it. So this says capture everything by value except for variable 1, which I want to capture by reference. So there's pretty much the full repertoire. The part I've always been confused about is why is it illegal to say equals variable? I've always wanted to be able to say that because to me it would be easier for me to remember its value if you put an equal. But no, if it's a value variable, you put nothing. You can't put an equal. Equal is only when it's a default for everything. All right. Only local variables can be captured. Capture only applies to non-static local variables. So within a member function, the data members can't be captured directly. They're not local variables. What you have to do is capture THIS. If you capture that, then you can have access to all the members. Or alternatively, you can just copy the value of some data member into a local and then capture that. Okay? You might prefer that because it's a little more straightforward. There's less happening implicitly. And as one of the reviewers of Scott's new book, I'm stealing one of his items here and previewing it for you, and I got his permission to do this. Avoid default capture modes. Even though they're part of the language, Scott actually recommends not to use these two guys because using them creates potential for some subtle behavior bugs. And there's a bunch of different situations he talks about. And eventually he just concludes, just don't use them. It's not something the compiler enforces. It's just one of Scott's pieces of advice. So take that for what it's worth. And when the book comes out, you can read all about it. All right, this is kind of cool. Neither C nor C++ allow you to declare functions inside of functions. Ironically, you can define a class inside of a function and then put functions in the class, but you can't have a function within a function directly. So this is an error. But lambdas give you a workaround. You can actually declare a lambda with auto, and that's the only way to give it a name because its type is unknown to you. It's some funky compiler-generated random gobbledygook, and you're not allowed to know what that is. So if you use auto, you don't have to know. The compiler just creates this name with an epsilon to represent the lambda, and then you can call it. So it effectively acts like a local function. Local functions via lambdas. Lambdas can get kind of complex to write. And so in C++ 14, the language supports generic lambdas, which basically turn lambdas into templates inside. I mean, lambdas are already resulting in a class being defined somewhere. And when you use auto as one of the parameters, now you're making it into a class template generated somewhere, basically. That's the idea. And it actually simplifies the code quite a bit. So what you used to have to say explicitly, that this thing takes a shared putter of string ref, right? We can reduce that to just const auto ref. Instead of const shared putter of string ref, we can just say const auto ref. It'll deduce auto to be shared putter of string, and it'll work. but it'll also work for different types. So the same call with different different ranges here will generate the code appropriate for that type of range. So the old version in C++ 11, if you have a lambda that takes a reference to a const vector of shared putters of string, you have to write it that way. In 14, you just reduce it to auto constref, and it figures out the type, and it works. And as a named lambda, it can be used with different containers and reused with those different containers. So it's still going to generate a new specialization each time. So that's pretty handy. All right, so here's some uses for lambdas, predicates for if the various if algorithms, whenever a comparator is required, custom deleters for the smart pointers, easy specification of predicates for condition variables when you're doing concurrency, callback functions that are just specified on the fly. All right. Lots of applications. All right. So we have about 15 minutes or less left for move semantics. This is going to be a challenge. In old C++, objects are copied a lot of the times when you don't really need for them to be copied, but the language really provided no easy way to do anything about it. So a mechanism known as the return value optimization is implemented in every half-decent compiler that will avoid the copying by playing some tricks with modifying parameter lists for you and having secret hidden parameters passed with points to the destination where the object's going to be constructed. And that's all well and good, and it works in a lot of the cases, but it also doesn't work in a lot of cases. So if you really want large objects to be efficiently passed from function to function, you can't rely on the RVO, which actually only works in one direction, called function passing back to caller, right? So for this example, I'm going to just create a set of classes that will serve as a platform. We have some type called big, and it's just something that takes a lot of resources. Here's a function that returns a big by value. So in old C++, and let's just not assume RVO for whatever reason, this is going to cause the construction of this temporary expression. A big is going to be constructed. Then theoretically, it's going to copy that into the return value. And the return value is going to be passed back to the caller and copied into some destination object. So there's potential for up to 3 constructors and 2 destructors that could get called. Now, in reality, for something this simple, the RVO and other optimizations will almost certainly reduce that. But with a bad quality compiler, that's the worst case scenario. And sometimes you kind of have to count on the worst case scenario, and you just don't know what sort of optimizations you're going to get. For an operator plus function, right, this is going to generate one object here that's the sum of these two. We know that there's a cost of that no matter what. But there might be an extra copy involved once this sum is calculated to pass it back. That's a separate copy operation. Then the actual internal local has to be destroyed. Then the temporary is copied over into sum, and then that temporary is destroyed. So again, there's a potential in the worst case of maybe up to 3 constructors and 2 destructors in those situations. So that's sort of the foundation for a mechanism that can reduce that potential cost. So there's ways you can attempt to solve the problem in old C++. You can return references instead of values. You can return pointers. Both of these are really problematic because there's memory management case issues that you may never be able to solve. You can use a smart pointer, and that's a lot better, but smart pointers have some overhead, especially things like shared putter. You might want to avoid that overhead. So ultimately, a new language facility needed to be introduced to deal with this. The key is if we know that the object being returned is a temporary, if the compiler can know that it's not going to be used anymore after it's being copied from, that situation can be optimized. Before I can talk about that, I have to talk about some terminology. And there's a lot of terminology on this, and I'm just keeping it to the bare minimum. L values and R values. How many of you think you know what those mean? Okay, at one point, what you're thinking they mean was probably correct or good enough. The meaning of those terms has evolved. So here's the way I'm going to define those terms. In new C++, an L value is something you can take the address of. So it may or may not even have a name. For example, star putter doesn't have a name, Putter has a name, but star putter doesn't have a name. But it's an L value to represent something that actually has a location. R values are things you can't take the address of. Usually they have no name. Howard probably knows the exception, if he's around somewhere. Things you can't take the address of. Literal constants, temporaries of various kinds, R values. So that's the basis of everything we're going to say from here on forward. C++11 introduces a new type. It is the R value reference. The syntax of declaring one is like the old-fashioned reference, except there's an extra ampersand. And yes, that's the recycling of yet another old token that meant something completely unrelated. But that's how it works in C++. If you declare a reference with 2 ampersands, it only can be used to bind to an R value. That's why it's called an R value reference. So here's an int, and here's an L value reference that can be bound to an L value I. Here's an R value reference that can be bound to an R value 10. Right? 10 has no address. It's an R value. Attempting to bind an L value to an R value reference is an error and won't compile. Attempt to bind an expression like I plus 10 to an R value reference is fine, because this is a temporary. It has no address. What's fn? It's a function returning by value. So what it returns is a temporary. It's an R value. Therefore, it's illegal to have an L value reference that can be bound to it. However, even in old C++, if it's an L value reference to const, it's legal. And the compiler plays a little game here. It actually takes that value that came back and squirrels it away in some memory location, creates an L value reference to address it, and gives you that. And it guarantees that the lifetime of the reference is at least as long. It guarantees the lifetime of that value that was squirreled away is at least as long as the lifetime of the reference returning to it. So it's a convenient way to get around some of the limitations. But there's some performance involved. The object is copied and then referred to. Right? But in C++11, you can have an R value reference that directly binds to a function's return value if it's a temporary, and that's fine. All right, so got the idea? L value references bind to L values. R value references bind to R values. C++ has always had copy operations. Copy constructor, copy assignment operator. Old hat. C++11 adds move operations, which are parallel to these. There's the move constructor, the move assignment operator. Notice the parameters are R value references. So they only bind to temporaries. And both would typically be no except. I'm just not dealing with that whole issue because we have enough to cover without dealing with that. So here is a little bit more fleshing out of this big class, showing all of the potentially generated functions. There's now 6 generated functions. Along with the original 4, the move operations are also potentially generated. And we'll go over when they're actually generated and when not. So default constructor, destructor. This is not a special function, right? This is just an ordinary constructor. Copy constructor, copy assignment, move construct, move assign. To make this example have some meaning, let's say that big has a data member B, which is where all the heft is. So this is some binary large object. Maybe it's a megabyte. Okay? And we're not worried about how it works. We just know that's part of this thing's composition. And then we'll throw a simple double in just to show that things that are potentially expensive are treated a little differently than things that are straightforward. That's our big class. So given these types of operations again, an operator plus that works on bigs, a munge function that does something to a big and returns a new value of a big, and then the original little factory function, we can sort of talk about how many actual constructions of full objects are involved in these various operations. In the old C++ case, remember I said there's up to 3 constructors and 2 destructors to do one of these simple types of operations. But with the move operations properly installed, all these operations are going to take, at the most, 1 full-scale creation. And when I say created, I don't mean number of constructors run. I mean number of actual, the data is populated operations are involved. So make big, at most is going to be 1. The addition and assignment is at most 1. Munge is still going to be 2 because it's munging the result of an addition. So the addition has one object that's created, and then munging itself, because it's doing a transformation and returning by value, is going to be potentially a second. So yes, there will be 2 created here. You can't do anything about it. Swap, when properly implemented, will have 0 objects actually created. It's just going to be exchanging guts. I'm going to shorten this next piece just because I don't have much time. But I actually learned about move semantics first from Scott Myers. I attended an early version of his overview of C++ 11. The first time I've ever saw it, and I thought, wow, this is cool. And then a day or 2 later, I'd forgotten most of what he said, except the basic idea. Some things are moved efficiently. But I couldn't sit down and write the code. A year goes by. I attend a talk that Dan Sachs and his son gave in Boston about move semantics. And then I understand it a lot better. But a week after that, I still couldn't sit down and actually write it. It didn't all gel. The thing that really made it gel for me is what I'm going to show you here. And I'm not saying it should do that for you. This just happened to be something that was the aha moment for me. So maybe there'll be a little of that rubs off. But I looked at the implementation of swap for the old C++ library. This is C++98 swap. And it's just a simple template that takes 2 references and does a shell game on them. Right? So it's exchanges through a temporary. There's 3 copy operations involved here. Not a big surprise, right? If you don't know anything else, that's how you swap 2 things. If you apply this function as written to the big class I just showed you, even with move support, you still have 3 copy operations that are going to happen. It's not enough to have move support. There's more required. The reason is that these are L-value references. And there's no way any of these operations are going to trigger functions that take R-value references as arguments, because they're not R-value references. They're L-value references. This is an ordinary copy construction, an ordinary copy assignment, an ordinary copy assignment, no matter how you implement that class. OK? So that's point 1. Now, this is the new C++ implementation of swap. The signature is the same. It kind of has to be, because the swap utility template is used universally. It can't change its interface. So it still accepts by L-value references, and it still is going to swap those things. But there's the addition of these little misleading things here called move. So move does not move anything. When you wrap something with a move, think of it as a cast to R value. That's exactly what it does. It generates no code. It simply says, treat this as an R value, and then go ahead and resolve this function call. So this becomes a move construction. This becomes a move assignment. And this becomes a move assignment. Presumably, that's the motivation for calling it move rather than R value cast. But it's a little confusing when you first see, because you think it's moving something. No, it's facilitating the moving of something by casting an expression to an R value so that the result will bind with a move operation. And that move operation is going to do things efficiently. That's what that means. Now, if you apply this version of swap to big, it swaps those things a whole lot more efficiently. But we're going to drill down and see the implementation. So here is the implementation of big's move assignment and move construction and move assignment. So for move construction, it simply takes the value of RHS as B, and it applies move to it, and then constructs its own B from it. That's going to do a move construction for B. For the double, we don't bother, because it's a double. You can't move a double any faster by moving it than you can by copying it. Make sense? So you could put move here. It would be a no op. It would basically have no effect on the code. Makes a big difference here. For move assignment, we move B and then assign the result to B. So that invokes move assignment on B. And then we just ordinarily assign X, and that takes care of that. That's it. Well, not quite. We haven't looked at what blob does. So this is more interesting when we drill down into what blob actually does. But this sets the stage to allow blob to do things right. So here's blob's class implementation for the move operations. Now we can see what actually happens in move construction. It's just taking, okay, here's the implementation, by the way. It's a raw pointer. Okay, just pretend that's not a raw pointer. It should be a unique putter. We're not worried about that. I'm trying to focus on this part. So this is going to just copy that pointer across. And then we take the original pointer of the source object and null it out. This is why this is a reference to non-const as opposed to a reference to const, because we're actually going to be modifying the right-hand side. We're going to render it essentially useless from this point on. This object, RHS, it's really not useful for anything after this, but to play nice with this mechanism, it must be possible to delete it, to destroy it, same thing, or to assign to it again. And as long as what you leave is something that can be destroyed or reassigned to, you're good. After all, it's a temporary. The whole idea is this is a temporary. It's probably just going to be destroyed. But there's some cases where it's not just destroyed. Whoops, that was it, right here. Right? After we move from it, we assign to it. Sometimes that happens. So you got to be prepared for that. That's part of the rules. All right, and for the move assignment operator, there's some debate about whether you need to bother with check for self-assignment. I'm just doing it. Release the old contents of the left-hand side. You always have to do that. And then do the moral equivalent of a copy construction. That's it. And now we've drilled down to the bottom. When everything works together, this becomes a really efficient mechanism. All right, I'm going to skip this because Scott already talked about universal references today, so I don't really have to. But I was just going to tell you what they are. The thing that's interesting about universal references is that they're a useful lie. There's a great talk that Scott gave that's available online. He said, I'm going to give you a lie, but it's a useful lie. And the useful lie is there's something called a universal reference. There isn't. There's no such thing in the standard. It's imaginary. It's just like there's no such thing called the STL in the standard. It doesn't exist. It's just all these components that have proliferated throughout the standard. Universal references are really a simplification of the mechanism of reference collapsing. So if you have something in a function template instantiation that ends up trying to declare an L-value reference to an L-value reference, the compiler turns that into just a regular L-value reference. And so on with these different combinations. And the only combinations of L-value and R-value references like this that result in an R-value reference is if they're both R-value references. Stefan Lavaveg says L-value references are infectious. So as long as there's one L-value reference, it dominates. And then when there isn't, we get an R-value reference. And universal references are just a way of modeling this. OK, so one more piece, and I guess we're probably officially out of time. But this is cool, so if you can hang around for this. What's our next thing happening? Is there anything scheduled at this point? Is there something at 4:30? 4:45? OK, so can you guys give me 5 minutes? OK, let's do it. What if you have a class with multiple data members, each of which is non-trivial? So you have a blob, and instead of a double, let's make it a string. So now we've got two objects, each of which have the ability to be copied or moved. And let's say they both have move support, right? Constructors now for one of these bigs are formulated through a blob and a string. But the user can provide any permutation of R values and L values. So it might be two L values, two R values, an L and an R, or an R and an L. The optimal implementation of each is different from all the others. So for this one, you just do a normal copy. For this one, you'd move the R value and move the other R value. For this one, you move the R value, but not the L value. For this one, you move the R value, but not the L value. What if there was a third one? How many functions do you need to cover all the bases? 8. For a fourth one, you're up to 16. Does not scale well. All right. So instead of doing that, use universal references and a function template. So this is a member function template constructor that takes two R-value references, but as Scott has suggested, we should think of these as universal references. In the case of a function template parameter, it's a universal reference if it's a reference, if it's an R-value reference without any adornment, no decoration. So no consts, no no other special qualifiers go there, and then it can be a universal reference. So just like we had this thing called move that we used to imply cast to rvalue, there's also something kind of similar called forward. And we can think of forward as a conditional cast to an rvalue. This is going to make B2 be passed to this constructor as an L value reference if B2 was passed in as an L value, and as an R value reference if B2 was passed in as an R value. Same for this one. This scales really, really well, because no matter how many of these you have, you just add one line for each new parameter. That's called perfect forwarding. I beg your pardon? Yes, because it wouldn't be a universal reference if it wasn't a template. If it was without the line with the template, this would just be an R value reference and that's it, and then this couldn't be made to work. So the whole intelligence of whether it's one or the other, like Schrodinger's cat, is based on being a template. So it can generate the different scenarios each time based on the calling, the arguments in the call site. Because each one's going to generate different functions. Of course, some can be reused. But there's a potential of up to 2 to the n different functions, different constructors getting generated. So you might think code bloat, but it's worth it here. This is so cool. You're willing to live with a little bit of code bloat. That's perfect. When do you move enable a type? Basically, if moving can be implemented faster than copying, you give it the move operations. If not, don't bother. It's that simple. Because then it'll just automatically revert to copying. If a piece of code says, move, but there is no move operation, it's not an error. It just uses the copy operation, as long as that's available. So provide copy operations and then provide move operations if they are useful. Some types are move only, like Uniqueputter has move constructor, move assignment, but not the copy versions. So special considerations to types like that. Remember the old rule of 3? How many of you have ever heard the rule of 3, right? Between destructor, copy constructor, and copy assignment operator, if you find yourself having to implement or even declare any of those, you should also declare the other 2. Well, now we can think about a rule of 5. If you need to declare any of destructor, copy operations, or move operations, you should declare the other 4 or implement them or whatever. There's also some people believe in the rule of 0, but that's a religious issue, so I'm not going to go into it. Basically, I like the rule of 5. And there's a special consideration. If you declare any of the 5, no move operations will be generated at all. No move operations will be generated. The copy operations are still generated for you in C++ 11, and I believe still in 14, or has that been deprecated? I don't know when the change takes place, but the standard committee made it really clear. They signaled that even though in 11 it'll still generate copy operations if you don't write them, in the future that's been deprecated. So if it's 14 or 17, I'm not sure, you have to observe this religiously. If you declare any of them, make sure to do the other 4. Even if it's just with equals delete or equals default. Still, be explicit. Let everybody know what you're thinking. Question?
Can you use default to get a default move?
Can you use default to get a default move constructor? I believe so. I remember reading something about that's not all that useful or something, but I believe it's legal. I'm not 100% sure. We're out of time, so I'm just going to stop with this little kind of overview of the evolution of the language. Is C++ too complicated? Anybody ever thought that? This is really getting complicated. If you actually look at the length of the language specification, C++ 98, I'm just talking language, not library, it was 309 pages. C++ 11 up to 424 pages, compared to Java, 606 pages for version 7. C#, 531 pages. Right? Now, some of this may have to do with the size of the font, and I don't know. But basically, it's not that dramatically more complicated. If anything, it's less complicated, right? Complexity versus what's really going to generate complications for you in your development process. I'd like to suggest a different way of evaluating what makes a language complicated. Does good code rely on undocumented idioms? How many gotchas show up? Can you say it in code, or do you have to write comments to explain what you're doing? Can you get high performance only by jumping through hoops? If you look at the evolution of C++, I think it really shows well if you apply these criteria to it. Okay, so maybe it's more complex internally, but the goal is to remove complications on the client side. And I think they've done that. So I started with a quote from Bjarne, and I'll just end with one here. That's not it. Or is it? No, I was close. There we go. So there's only two kinds of languages, the ones people complain about and the ones nobody uses. We're done. Thank you for hanging in there for the extra